time division multiplexing system is shown below. The bandwidth of the channel required for accommodating the multiplexed signal if each signal is sampled at its own Nyquist rate. So if we want to Nyquist, because see all the signals are multiples of 2, so the Nyquist rate for this one is 4 kilohertz, this is 8 kilohertz, this is 20 kilohertz, this is 16 kilohertz, this is 24 kilohertz. So if we take 4 kilohertz, so first signal, we can divide this into 2 signals. 2 kilohertz signal is sampled at its own Nyquist rate if we sample once. For the next signal, suppose if we keep the sampling frequency as 4 kilohertz, suppose fs is 4 kilohertz I am taking. So the first signal must be sampled only once per second. Once per means the signal must be sampled within sampling time only once. But the 4 kHz sampled signal must be sampled twice. 10 kHz must be sampled 5 times. This is 4 times and this is 6 times. So if we combine, that is 1 plus 2 plus 5 plus 4 plus 6, which is nothing but 8, 12, 18 signals. So the number of the bandwidth is nothing but 18 into fs in, that is 4 kilohertz, which is equals to 72 kilohertz. That is option B is correct. A CDMA system has spreading code rate of 3.84 megachips per second and user data rate is 15 kbps and required SNR to get this performance is 90 with the number of users served by one cell is. Here coding gain is nothing but 3.84 into 10 power 6 divided by 15 into 10 power 3, which is equals to 256. That is 256 for k minus 1 users, that is x for 1 user, that is x equals to 256 minus divided by k minus 1. Here 10 log ax is nothing but 9 dB, which is x equals to 10 power 0.9. So k is nothing but 256 10 power 0.9 plus 1, which is equals to 33. That is each cell serves 33 users, that is option B is correct. Impedance for the transmission line system shown below. Here Zn dash is the input impedance for the quarter wave transmission line. For that one, ZL by Z0 square by ZL. Z0 square is 50 into 50. ZL is 100. So it is 25 ohms. And for the Zn is equals to Zn dash, because the length of the transmission line is lambda by 2, so which reflects the output impedance towards the input impedance, which is 25 ohms. That is option C is correct. Standing wave pattern in a lossless transmission line with characteristic impedance of 50 ohms and the resistive load is shown below. The value of the reflected power is if the incident power is S1. Here power reflected by power incident is equals to the gamma square, that is the magnitude of the reflection coefficient. Here the reflection coefficient is nothing but S minus 1 by S plus 1, where S is the VSWR, that is Vmax by Vmin, which is 4. So gamma is going to be 4 minus 1 by 4 plus 1, that is 3 by 5, which is 9 by 25, which is equals to which is equals to 0.36. So power reflected is equals to 0.36 into 2, that is incident power is 2 watts as per the data given in the question. So it is going to be 0.72 watts. That is option B is correct. Receiver is r kilometers away from the transmitter. What is the distance that this person must move further to detect a 3 dB decrease in signal strength? So PR, that is power at or distance at a distance of 4 kilometers, is P naught, suppose, that is transmitted power divided by 4 pi r square. This is this one. PR plus X is nothing but P naught by 2 because of 3 dB decrease in signal strength. In power it is going to be half, so PT by 4 pi, it's going to this distance. So if we divide equation 1 divided by equation 2, P naught divided by P naught by 2, 4 pi r plus x whole square by r square, that is 2 is equals to root 2 is equals to r plus x by r. From this, r plus x equals to root 2 r, x is equals to 0.414 r, and that is option C is correct. Resistance of a lambda by 2 dipole antenna is 50 ohms, and find the efficiency of the dipole antenna. Here efficiency of a dipole antenna is given as loss resistance divided by the loss resistance plus radiation resistance, that is here radiation resistance, or radiation divided by R loss plus R radiation. For lambda by 2 dipole antenna, the radiation resistance is going to be 73 ohms. 50 plus 73 ohms, which is equals to 0.6, that is option B is correct. Wave propagates from one medium whose wave impedance is N1 and another medium having a wave impedance of N2. The ratio of transmitted power to incident power if N2 is equals to 3N1. Here P transmitted by P incident is equals to 1 minus gamma square. Here gamma is nothing but N2 minus N1 by N2 plus N1. Here N2 is 3N1. So 2N1 divided by 4N1, that is 1 by 2. So which is 1 by 1 minus 4, which is 3 by 4. That is option A is correct. RLC circuit, Vs is 400 volts, which is RMS value, and R equals to 20 ohms, and inductive reactance is 40 ohms, and capacitive reactance is 40 ohms. We have to calculate the Q factor of the series RLC circuit. Here the data itself they have given as XL equals to XC. That means the circuit is at resonance. In that case, the Q factor is omega naught L by R. Omega naught L is nothing but XL by R. XL is 40 divided by 20, which is equals to 2. That is option A is correct. Comes to the second part B, the voltage across the inductor. VL is nothing but IXL into 90 degrees. Here XL is 40. I is nothing but 400 volts VRMS divided by 20, that is 20, which is nothing but 20 into 40 at 90 degrees, which is 800 at 90 degrees. That is option A is correct.
It is given that from a pack of cards, 2 cards are drawn at random. Now we have to find the probability that both the cards will be king if the first card is not replaced. Now we know that there will be 4 kings out of 52 cards. So in the first pick, what is the probability? Out of total 52, we are taking 1 card, so 52C1. And what is the probability that it is a king? There are 1 chance out of 4, 4C1. So which is nothing but 4 by 52. This is in the first pick. But in the second pick, what is he saying? The card is not replaced. If the card is not replaced, there will be only 51 cards here and 3 kings, because already we have taken 1 king. So what is the probability? The next probability will be 3 by 51, which is nothing but 1 by 221. That is option D.